Alright, welcome back everybody. In this video we're going to look at the last couple of examples from the derivatives of vector-valued functions lesson. We start here with some basic definitions of velocity, speed, acceleration, and direction of motion as they pertain to a position vector of a particle. And these are really, the first three should be fairly obvious to us. The velocity vector is going to be the derivative of the position vector, which ties in completely with what we know so far about velocity and position. The speed vector is going, or the speed is going to be the magnitude of the velocity vector. So it's just going to be a length. That's going to be a scalar value. The acceleration is going to be the derivative of the velocity function. And so the acceleration vector we can find by just taking the second derivative of the position vector. And this last one, the direction of motion, is something that you may not really be thinking about, but we've hinted at it a little bit in some earlier videos. The direction of motion is a unit vector that describes the direction in which a vector-valued function is traveling. It takes the velocity vector and divides it by the speed vector to get a unit vector that shows the relative components as far as, how much of the direction goes in the x direction and how much of it goes in the y direction. Alright, let's look at example 4 here. We have a position vector of a particle in the plane at time t. We're supposed to find a few characteristics here. First, we're supposed to find the velocity vector. In order to do that, we're just going to find the derivative of the position vector. And so the velocity vector is going to be, and now I just need to take the derivatives of the components of I and j. So this is going to be negative 4 sine of t I plus the square root of 2 cosine of t j. That's my velocity vector. My acceleration vector is the derivative of the velocity vector, so I'll take the derivatives of those components again. It's going to be negative 4 cosine of t I plus negative square root of 2 sine of t j. Alright, next we're supposed to find the velocity at time equals pi over 4. In order to do that, we're just going to substitute pi over 4 into the vector-valued function for the velocity. So we've got negative 4 sine of pi over 4. Sine of pi over 4 is root 2 over 2. So this is going to just be negative 2 root 2 I. And the cosine of pi over 4 is root 2 over 2. So we've got root 2 times root 2 over 2. That's just going to be 1 j. And I don't need to write that 1 there. I could just write a plus j on the end there. But there's the velocity vector at time pi over 4. The acceleration vector at time pi over 4, I'm just going to substitute into my acceleration vector function. And so I put pi over 4 in there, and we're going to have, let's see, negative 4 times root 2 over 2. That's going to be negative 2 root 2 I and negative 1 j. Alright, continuing on here. The speed at time pi over 4 is going to be the magnitude of the velocity vector. We already have the velocity vector at time pi over 4. So in order to find its magnitude, we're just going to take the absolute value of negative 2 root 2 squared plus 1 squared. And so the speed is going to be, let's see, that's 4 times 2, that's 8, plus 1. So the speed, oops, I forgot my square root in there. Square root of 9, which is going to be 3, is going to be my speed. And now the direction of motion at time pi over 4. All I'm going to do is take my velocity vector and divide it by the speed, and so the direction of motion is going to be negative 2 root 2 over 3 I plus 1/3 j. And this is a unit vector that describes the relative magnitudes of each of the components. All right. So that's it for example 4. On to example 5. This is a free response number 2 from the 2012 AP Calculus BC exam. So it is a calculator section, or a calculator problem. For t greater than or equal to 0, a particle is moving along a curve so that its position at time t is x of t, y of t. At time t equals 2, the particle is at position 1, 5. It is known that dx dt equals the square root of t plus 2 over e to the t, and dy dt equals sine squared of t. All right. First, is the horizontal movement of the particle to the left or to the right at time t equals 2? Explain your answer. All right. So in order to find the horizontal movement, well, the horizontal movement is based off of the change in x with respect to time. So the question is this moving to the left or to the right at time 2? And so we're going to find dx dt at time 2, and we'll put 2 in here, and so that's going to be the square root of 4 over e squared. This is positive, so it's going to be moving to the right. Moving to the right, because dx dt is greater than 0. And then we're supposed to find the slope of the path of the particle at time t equals 2. The slope of the path, so we're just looking for dy dx. So dy dx at time 2 is dy dt, so that's the sine squared of 2. That's the worst 2 I've ever written in my life. It's the sine squared of 2 over, and we already know that this is square root of 4 over e squared. Do I really want to write square root of 4? How about just 2 over e squared? I struggle sometimes in the morning. That's 2 over e squared. And so the slope of the path of the particle, if I go ahead and calculate this, it's going to be the sine of 2 quantity squared times e squared divided by 2, and we get 3.055 for the slope of the path of the particle. All right. Part C here. Find the speed of the particle at time t equals 4. Find the acceleration vector of the particle at time t equals 4. Okay, so the speed is going to be equal to the magnitude of the velocity vector. We have the velocity vector because we have these components up here for dx dt and dy dt for the path of the particle. So, in order to find the speed of the particle, we're just going to find the square root of dx dt evaluated at t equals 4. We're going to square that, plus dy dt evaluated at time 4. We're going to square that. We'll take the square root of that, and that's going to be equal to the speed. Okay, so the speed is going to be the square root of the quantity square root of 4 plus 2 I need another parenthesis in there. No, I don't. My gosh. Okay. Square root of 4 plus 2 over e to the 4th quantity squared plus sine of 4 quantity squared quantity squared close the square root. And we get 0.575 for the speed. And then we need the acceleration vector at time t equals 4. Well, in order to do that, we just, we don't want to take these derivatives by hand. That's too much here. But what I can do is I can use the numerical derivative function to take the derivative of dx dt at time 4. So we want the derivative of square root of t plus 2 over e to the t with respect to t at time 4. We get negative 0.0411. And then we want the derivative of the y component vector, sine of t, quantity squared, with respect to t, evaluated at 4, 0.989. And there's the acceleration vector at time 4. Now I could have found the general acceleration vector valued function by taking the derivatives of each of these components, but that's just too much work in this context. Since this is a calculator problem, let's use the numerical derivative. Alright, that's the end of this video and the end of this lesson. See you guys next time. Have a great rest of your day.